we're going to be talking about the priority queue today. The priority queue is just a queue that pulls out the thing with the priority and not just the thing that's first in line. So we're going to be doing this using the heap data structure, and the heap data structure is like a tree, except it's a little different. The heap can be implemented multiple ways, but we're going to be implementing it using a dynamic array, which we can grow. So this is used with memory and operating systems. One example I can think of is like the scheduler in the operating system deciding which process to send to the CPU. So that's where this priority queue is going to be useful. So like I said, we're going to be using the heap. There's two types of heaps that we're going to be looking at. There's the max heap and the min heap. We're going to be implementing the max heap, but it's good to know the difference. So the max heap just stores the max at the top, and the min stores the min at the top. So yeah, and then each layer increases or decreases depending on which heap you're talking about. We're going to be implementing this through the dynamic array, and how we're going to do this is with these two equations. So you can find the left child of any given index using this equation, 2n plus 1, and then the right child using 2n plus 2. So if we look here, 7 is our root, so that's always going to be at 0. Root's always at 0. And then if you do 2 times 0 plus 1 is 1, so 5 should be to the left of 7, and it is. And then 2n plus 2 is 2, so 0's right child is index 2, which is 6. Right there, and you can do that for every single one of these and it'll give you the right one. So we're going to talk about our two main functions, which are insert and delete. So for insert, we need to check first off if we need to increase the size of the array. As you can see, this array has 9 positions, but if it only had 7 and it was fully filled, then we would need to copy everything in that and move it to a bigger array. And how we're going to do that is with two variables called size and capacity, and if they're equal to each other, then we'll increase. We'll talk about that later. And then we're going to insert the first available into the first available position, so we would be inserting the number into 7 in this case. And then we're going to increase the size variable by 1. And then we're going to do this thing called heapifying up. So let's work through this with an example. So let's say we want to add the number 8. No, let's do like something less, 6. Let's add 6. So we put it in the first available position, like that. And if we're thinking about it as a tree, it's always going to be pushed to the far left. So this is the far left, 6. And then we're going to do that thing called heapifying up. And all this is doing is checking with the parent to see if it's bigger, if we're looking at a max heap. If we're looking at a min heap, it would check if it's smaller. So 6 is greater than 4, so we need to move 6 and switch it with 4, like that. And then 6 is greater than 5, so we switch it with 5. And then 6 is less than 7, so we just keep it where it's at. And that's called heapifying up. Let's talk about the delete. So the delete simply removes the root node and replaces it with whatever's in the last index of the array. Well, the last filled index of the array. And then we decrease the size and we do this thing called heapifying down, which, as you can guess, does the exact opposite of heapifying up. So if we wanted to remove from the queue, so we're removing the highest priority, which is at the root, so we get rid of it. And then we replace it with what's at the last position. So this would be all different, so let's just look at the tree. So the last position in the array would be 4. So we move that to the top, and then we do heapifying down. So we're gonna compare it to the children, whichever one's bigger in this case, because we're working with max heap. So we compare it to 6, and it's less than, so we have to switch it. But we have to look at our right child to see if the right's bigger, which is not, so we're just going to switch it with the left. Like that, and then like that. And then we do the same thing until it's in the right position, so 5 to 4, 5's bigger, so we switch it. Alright, and that's how we heapify down. So those are the two main functions. Using the dynamic array, this will give us a low space complexity. So let's look at the code. Here's our header file. I'm just using IOStream in it, and I'm implementing this as a class. So here's our size and capacity. Our size is going to hold how many items we have in the data structure, and then our capacity is going to be the size of the array. Alright, and then we have a bunch of helper functions which just check the index of the right and left child or parent, and then we check if they have those, and then we get the value at those places. And then we have a function called swap. It just swaps two indices, so that's going to be useful in our heapify up and heapify down. And then we have a bool function that checks if we need to actually increase the size of the array. This is just going to check if size is equal to capacity. And then we have an isEmpty that just checks if size is equal to 0. We have a grow heap, which is going to copy all the items in the current array into a bigger array because the current array is full. And this will execute when the need to increase heap size is true. And then we have our heapify up and heapify down. We'll look at those. And then here in our public we have our actual array, which is just a dynamic array size of capacity, which will be set in the constructor. Here's our constructor. Constructor will set the size equal to 0 and the capacity equal to 10. 10 is just an arbitrary number. And then peak will return whatever's at the root, and then insert is going to do what we talked about. Pull is our delete function, so it's going to do what we talked about. And then print's going to print a pre-ordered traversal of the tree. So if we look at the implementation, we're just going to go through the main stuff. So let's look at the heapify up and heapify down. We're setting a integer variable equal to the last position in the array. Well, that's not exactly true. We're setting it to the last filled position in the array, and then we're doing while there's a parent and the parent is less than the current, then we swap them and set the last equal to whatever the parent index was. So that's all that's doing, and it's doing that in a while loop, so we can do it multiple times. And then in the heapify down, we're setting the first integer variable equal to 0 because that's the root. And then we're doing a while loop while there's a left child, and then we're setting a larger index, so we're checking whether the right or left index is the larger one so we can switch them properly. And then we check if the larger index is greater than the current one, and then if it is, then we just switch them, and then we set the first equal to that index. Alright, here's the insert. So we're passing in a key. We're checking if it's empty. If it is empty, then we're just setting it as the root at 0 and then increasing the size by 1. If it's not empty, then we're going to check if we need to add room to the heap using that need to increase heap size, and then we're using the grow heap. And then we're setting the index of size equal to the key, because size is always going to be one more than the last filled position in the array, and then we're increasing the size by 1, and then we're just sorting the heap by heapifying up. And then for our delete function, we're setting the root as the 0 position in the array, because that's where the root's always going to be. We're just doing this so that we can return the root, because you can see we're returning an integer. And then we're switching the root with the last filled position in the array. Then we're decreasing the size and heapifying down, and then I'm returning the root so I can use it in the main. Alright, so that's all that's doing. My main is pretty arbitrary. It's just using some test values. So let's go ahead and run that. And this is all it's doing. It's adding these values and then printing it, and then it's deleting each one. So this is a max heap, so we should see the highest number being deleted first. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 shows that the highest number, the highest priority is being pulled first. And then same thing with our second test numbers. So you can see it's decreasing in decreasing order. So that's the heap data structure, and more specifically the priority queue. Try implementing this on your own. The source code will be on a Git repository. Thanks for watching. Catch you later.